Hello again. We will continue in this session with chapter 2, and we will focus this time on the mechanical properties of fibers. Well, I need to point out something that's very important, and that is the mechanical properties of fibers represent a series of characteristics that, although we're going to discuss it in relation to fibers in this session, but they are applicable to all types of materials. So we need to pay some attention to these properties, because anything we will cover in this chapter or in this session of this chapter will apply to yarns and fabrics as well. The mechanical behavior of material has, or we can uniquely define the mechanical behavior of any material using a set of parameters and some profiles that are applicable to any material. So we need to pay a great deal of attention, because whatever we cover here, we will not cover it when we talk about yarn strength, for example, because again, the parameters and the curves and everything we will show will be applicable there. Mechanical properties, mechanical characteristics. There are many mechanical characteristics of material. The tensile characteristics, which are the characteristic that we see under tension. The torsional characteristics, those that we can detect under torsion or twisting of material. Bending, another mode of deformation. In general, when textile material is in use, or if it is in processing, it may be subject or subjected to various types of external loading. The material may be under tension, it may be under compression, it may be under bending or shear. And of course, a derivative from the shear deformation, torsion is another form to express shear. So these are the different modes of deformation that we typically see either during processing of the textile material or during the use of textile materials. And we see these different types of deformation at different levels of loading, from very low level of loading when somebody just touch the material and by hand and handle the material, and all the way in applications where the material has to be subject to tremendous stresses by washing and tumbling and drying and all of that. And during processing, of course, we see all sources of deformation. We can look at the fiber flow and see that in our process of manipulating the fibers to make a yarn out of it, we have to use different modes of deformation and different types of stresses. As a matter of fact, fibers during processing are subject to almost all modes of deformation. They are being stretched, they are being compressed, they are being pressed, they are being bent, they are being twisted, and they are being rubbed against one another and against different solid surfaces during processing. You take the yarn and you just take a look at the weaving preparation, and you will see the tremendous stresses of various modes that the yarn is subject to, all the way to the weaving process. To me, the loom or the weaving mechanism is the best demonstration of multiple stress modes, where the yarn is stretched, bent, compressed, rubbed against different parts of the loom. So mechanical stresses are extremely important. Mechanical behavior of material is extremely important. Even on the fabric mode, fabric finishing and dyeing, the fabric has to be under tension. The fabric bend all the way as we wind it and unwind it. The fabric rub against different solids. So our textile materials have their share of mechanical stresses all the way from the fiber to the fabric, and certainly in the end uses. So that is why we need to pay some attention, because I cannot imagine any contract of purchasing or selling fibers, yarns, or fabrics that would not include at least one or two mechanical parameters characterizing or specifying the material behavior. So again, this is a very important part of this chapter, and hopefully we will provide you with some information that will add to what you already know about the mechanical properties of textile materials. You need to keep in mind, as we mentioned in an early session, that textile materials in general are categorized as flexible materials. And the importance of this point is that our material in general does not require tremendous level of loading to be deformed. And that's why we call it flexible material. So with that, we will start discussing the different modes of deformation and the different types of mechanical characteristics. The first type is the tensile properties. And this is by far the most important characteristic, or the most important mechanical characteristic of textile material. As I said before, all contracts and all specifications of textile materials must include the strength of material, particularly under tension. That's what we meant by tensile properties. What we see here is a material. This can be a yarn, or can be a fiber, or even a piece of fabric of a length, original length, say L0, and it has a cross-sectional area A, and we are applying an axial tensile load, axial along the axis of the material, and this is a typical situation that we quite often see in our laboratory. For a fiber, for a yarn, for a fabric, it's really basically the same concept. There are different ways that we stretch the material under tension. We can stretch the material using the so-called constant rate of loading. That means the load changes over increments of time, or constant rate of elongation. That's we stretch or we extend the material at a constant rate with time, or constant rate of traverse, meaning that we drive one clamp at a constant speed as we stretch the material. But in any case, as we stretch the material along its axis, what happens there is that a tension builds up, because the material is trying to resist the external loading. So stresses, or internal stresses, will build up inside the material, and different materials will react differently to the same level of loading. And as we continue the process of stretching the material, then ultimately the material is going to take no more, and the material will rupture or break. So this is the general phenomena that we see in any tensile test, and I don't need to elaborate on that any further, because all of you have seen a tensile test for any one of the familiar textile materials, fibers, yarns, or fabrics. How we describe this phenomena, how we describe the tensile mechanism, how we describe the buildup of the tension, we commonly describe that by a number of parameters. If we stretch a material, as we see here, as a result of stretching this material or applying this axial load, there will be an extension or an increase in the length of the material, as you see here. So the original length is L0, and the extension is delta L, or an increment of length. So this is not something that we all familiar with. So the load we apply is F. This load, if we divide it by the area of cross-section, will give us what we call it the engineering stress. So if you hear the term engineering stress, it is the axial load divided by the area of cross-section. And as you know, we don't typically measure the area of cross-section or the diameter of material. We discussed in the last session that we use indirect measures of the area or the fineness of material. We use the tex, we use the denier, and so on. So we'll have to come up with our own term describing stress, and we will see that shortly. But for right now, the engineering stress is the axial load divided by the area of cross-section. We also have the elongation, or we commonly in our industry call it elongation. And elongation really could be expressed in many different ways. I mean, just the increase in length in centimeter or millimeter could be considered an elongation or extension, to be more specific here. But if we divide that increase in length by the original length, we will get what we call it strain. And if we multiply that by 100, we will get the percentage elongation or the percentage extension, or what's commonly known among mechanical engineers as the strain of material. So we have two basic definitions, or two basic parameters that actually describe the tensile loading. One is the tensile stress defined by the load we applying divided by the area of cross-section, and the other is the elongation percent, or the strain defined by the increase in the length divided by the original length. And we can express that in percentage, as you see here. These are basic parameters. To go further in that, we have to describe the phenomena graphically as well. And typically we use the so-called load elongation curve, which describes the process of the tension buildup as we stretch the material all the way to the breaking point. So at this point of time where the material ruptures completely or break, we have the end of the load elongation curve, or the end of the stress-strain curve, as we will discuss shortly. So the tension buildup during the tensile test can be characterized by a curve. All advanced testing techniques today produce such a curve, and the curve continues all the way up to the breaking point. Now, textile material in general is characterized by a phenomenon that we often overlook, or sometimes because of the speed of the test, we don't get to see it very closely. And that is our material do not typically break sharply. In other words, we don't have a sharp rupture of the material, especially if we are talking about a yarn or fabric, because the yarn or the fabric will typically break at the weakest point, and after that there is other elements in the structure of the yarn. There are other fibers in the yarn, there are other yarn in the fabric that continue to support the resistance to the tensile loading. So if one would slow down the test, one can see that even after the breaking point, you will see some kind of stick-slip pattern describing or characterizing the final process of the rupture or the breakage of our material. I don't know how many of you have performed a tearing test on fabric. This is even more obvious in the tearing. I'm talking about the stick slip phenomena. So we need to keep that in mind. We need to keep in mind that although our material looks very much like in behavior under tensile loading, looks like very much like many other types of material, but we do have some unique characteristics. Unique, I mean they are actually unique to our material, to the flexible structures that we dealing with all the time. Let us now take a look at the so-called load elongation curve, the curve that describes the phenomena. Now, typically speaking, we have the vertical axis representing the load and the horizontal axis representing the elongation, or the increase in length of the sample. Most testers will give you the load in gram or newton or pound force, and the elongation in length, which is the increase in length. Many will give you the load as well as the elongation percent, meaning the increase in length divided by the original length. But let us take a closer look at what happened during the breakage. Typically speaking, most of our material will exhibit a linear trend in the initial stage of stretching. So as we stretch the material, initially speaking, we will get a linear trend that is almost a straight line. Now that straight line may be very short, may be very long. Quite often it goes unnoticed in many cases where the material tend to deform non-linearly or plastically at very, very small level of loading. So up to that point here, we can imagine that if we remove the load, the material will recover or will spring back to its original length. So if we stretch the material up to some point, the material and remove the load, the material will recover. We will call that the elastic limit of material under tension. And after that, if we exceed that elastic limit, the material will typically follow a nonlinear trend of tension build up and the elongation corresponding to that, all the way up to the rupture point or the breaking point. So this is a typical curve that really covers all sort of behavior during the tensile loading. Now, that doesn't mean that every single fiber or every single yarn will follow that trend. The only thing that is common in all material is that at some point of time the material will rupture under tensile loading. Okay, but some material may follow straight line all the way. Some material may follow a steep linear, non-linear effect. Others may go in different direction. So we will see later on some examples of stress, strain, or load elongation curves. But for right now, let us use this as our general reference of tensile load elongation curve. Now, let us take another look at this curve and try to describe some of the parameters that, or some of the important information that this curve reveals. And I need to stress that because just about every textile mill has an Inestron or Tensor Rapid or TensorJet, and all of these testers can provide you with a load elongation or some form of load elongation behavior. And quite often you get the load elongation curve. And if you have this curve, and despite the fact that you are given many numerical parameters, the curve by itself tells the whole story about the yarn or the fiber or the fabric. So it's extremely important, in addition to looking at the numerical values described in the tensile test, is to also look at the behavior using the load elongation curve. Typically speaking, at the rupture point, we can obtain the load at which the material break, and this is what we call it the breaking load or the strength of material. So what is a strength of material? It is the load at which the material break. So if we go at the breaking point and we simply take a horizontal line like I did here that will cut the vertical axis at some point, this point will be called the breaking load or the strength. If on the other hand at the same breaking point we take a vertical line, it will cut the horizontal axis at a point that we call the breaking elongation. Okay, so this is the basic idea here, is at the breaking point we can obtain the breaking load or the strength of material and the breaking elongation or the elongation at which the material break. Okay, and by far these are the two most commonly used parameters of strength of material in our industry. Just about everybody, just about every contract specifies at least one of these two parameters. Certainly the strength. Some other contracts may specify both strength and elongation. But these are the two most commonly used parameters of material strength under tension. But these two parameters, although they are extremely important, they do not tell the whole story about the tensile behavior of material. And that's very important to emphasize here, because particularly or especially with yarn and fabric, you must know the whole story, especially if you are developing a new fabric or you are trying to improve the tensile behavior of material. So let's look at some other characteristics or some other parameters that the load elongation can describe for us. The yield point. I mentioned a minute ago that most materials would follow a linear trend in the beginning until they reach some point beyond which they follow a nonlinear type of deformation. And I also said that up to that point, the material will spring back or will recover its original dimensions upon removal of the load. We will call this point in general the elastic limit point or the yield point. Yield means beyond this point, the material may yield largely permanently. In other words, if you try to remove the load beyond this point, the material will not fully recover all its original dimensions, but rather it will recover some of the original dimensions. And this point is extremely important because which parameter should we care about? Is it really the breaking point or the yield point? Now, engineers in designing any structure, the design is always based on the yield point. The stress that is indicated or the capacity that's indicated on a bridge as you pass that bridge driving your truck or your car is certainly not the braking stress of the bridge, but rather a value that's far less than the breaking point at which or above which the bridge will yield. And that's really the whole idea here. And I think we need to understand that as we load the material during processing, we should never ever exceed the yield point. We should never exceed the elastic limit. And I think that, or I believe that all machine makers and all people that design and develop machines that will handle textile materials make sure that this point is well taken care of. Meaning that a technology that will load the textile material beyond its yield point is not a good technology. Okay, so they make sure as they stress the yarn or stretch the yarn during spinning, or as they stretch the yarn during weaving or knitting, that the force or the load applied is less than the yield point, because certainly you don't want the yarn to yield. You don't want the yarn to suffer permanent deformation. Now, as important as this point is, I don't see many people using this this parameter here. But if you chose to use it, it's there. It is produced by your testing instrument. And of course, just like we did with the breaking point, where we obtained the breaking load by drawing that horizontal line and the breaking elongation by drawing the vertical line, we can do that with the yield point. If I go horizontally at the yield point, I will get the yield load, and if I go vertically, I will get the yield elongation. The only catch here is what I draw here is a curve that has a distinguished yield point, meaning that you can easily or visually see the yield point. Now, in many cases, you may actually see the curve doing this or doing that with an obscure yield point. And in this case, we have to approximate the yield point. And there are ways associated with each testing technique that can show you how to determine or at least approximate or estimate the yield point in a curve that the yield point is not clear in it.